Good morning. Is anyone here does not understand Portuguese? So, okay, I'll continue em português. Bom dia, pessoal. Bem, que bom que estão aqui depois do jantar de ontem. Eu ainda estou digerindo. Mas foi ótimo. Obrigado por comparecer lá e obrigado por comparecer hoje aqui. Hoje a gente vai ter 2 plenárias pela manhã. E antes de chamar o próximo plenarista, eu vou só lembrar que hoje tem a foto do evento. Então vai ser às 4 horas, a hora do começo do coffee break mesmo, aproveitar que está todo mundo lá. E vai ser ali perto do departamento de matemática. As atividades à tarde são no departamento de matemática. Vai ser num teatro de arena que tem ali próximo. O departamento de matemática é essa bolinha verde aqui. Então, a foto vai ser, se não estiver chovendo, a foto vai ser ao ar livre, ali perto. Aí a gente conduz vocês até lá. Só que só ficar atentos com a hora, porque vai ser... Tem o intervalo do coffee break e as atividades voltam às 4h30. Então, o momento da foto vai ser às 4, no máximo 4h10. A gente já quer ter tirado essa foto, para vocês poderem aproveitar o coffee break e as sessões que vêm depois. Ok? Se estiver chovendo, tem um plano B para a foto, que é no meio do caminho, para esse ponto amarelo. Então, vai ser tudo ali por perto. Beleza? Então, eu vou chamar o Chair, que vai apresentar o nosso próximo plenarista. Obrigado, Yuri.
Hello, everyone. I think this is going to be recorded, so I will speak in English, so that anyone watching the video later on can appreciate that. So it is a great pleasure and honor to introduce you to the speaker of this morning, the mechanics session, Gabriel Gatica from the University of Concepción in Chile. So I was telling him on the way that I phoned the Chilean police service and I got all the details about his life here in hand, so I'm going to list some to you so that you know our speaker a little bit better. So Gabriel graduated in mathematics in 1980 at the University of Concepción, and later on went on to get the degree of mathematics engineering at the same university, where he also got his master's degree. And then he went on to get his PhD at the University of Delaware at the United States in 1989. He then became a full professor in numerical analysis of partial differential equations at the University of Concepción in Chile. And he did a great job there, founding what is today the CIMA, Centro de Investigación en Ingeniería Matemática. Yes, and that's it, right? So he has been associate editor of several journals. I managed to count 6. One of which was the SciEM Journal of Numerical Analysis, which is the most prestigious journal in the area. He has supervised around 20 PhD students and 30 other students in undergrad and master's theses. He has been, of course, invited speaker in several international conferences, and of course this is the most important one he has ever been. So he's now increasing his CV on that matter. And he is interested in showing his research areas are existence and unicity of continuous and discrete solutions of partial differential equations, providing a priori and a posteriori error bounds for numerical schemes. He's also interested in fully discrete methods and the implementation of efficient computational algorithms in problems involving fluid dynamics, as he's going to tell us today, solid mechanics, electromagnetism, and of course potential theory. So I'd like to welcome Gabriel. Thank you so much for coming, Gabriel. It is a great honor to have you here. Thank you.
Thank you for, first of all, for the invitation and for this very fake introduction. So thank you all for coming. A very nice city, actually. I was telling Yuri, this is my first time in Brazil. My first time in a, well, I was in the airport, but that doesn't count. And it's very, very beautiful to see so many green areas all around the city. So it's very impressive. So I'm enjoying this stay. All right, what I want to, not working. All right. This is a joint work with several people from Concepcion, from other places, undergrad student, PhD student, and collaborators. So the main idea of the talk is to show some aspect, not all of them, because there is no much time, of the analysis of nonlinear and some coupled nonlinear problems in fluid mechanics by means of Banach spaces, make formulations. So in order to do that, I will refer briefly to three different model problems: the coupled Darcy and Heat equations, the Navier-Stokes-Brinkmann problem, and the chemotaxis Navier-Stokes problem. So let me begin with some preliminaries, just basic things to remember what the Lebesgue space is, right? The measurable functions with the power T bounded, the usual Holder inequality relating the S and the T conjugate, so you get this inequality that the integral of V times W is less than or equal to the norm of B Ls times the norm of W Lt. And certainly the particular case that you have a T equal S equal 2, you have the well-known Cauchy-Schwarz inequality. In addition, we are going to use some concept related to Sobolev spaces, in particular H1, which are the distributions in L2 whose gradient is also in L2 vector, H div R, which are the vectors in L2 whose divergence in the distributional sense, it's also in it's in LR. R is greater than 2n divided by n plus 2, and that the reason of that, something I'm going to say next. And also we remember what W1S is, the distributions in LS with gradient in LS as well. And then HT div T, which are the tensors in the vectors in LT with divergence in LT, again in the distributional sense. All right. These are very common spaces, particular this one and this one here. For the weak formulations, I'm going to discuss in the next sections. So the reason for this R greater than 2n n plus 2 is because of this integration by part formula that hold in those cases. It has to do with the fact that H1 is included continuously in LT for any t greater than or equal to 1, but only in R2. In R3, it becomes 2n divided by n plus 2, 6/5. That's because of an embedding of Sobolev spaces. And then you have this integration by part formula relating a vector function in H div R with a scalar function in H1. And then when you extend this to the more general case, Ht div T, then you have a similar integration by part formula, but holding now for T for tau in Ht div T and a B in W1S. And that reason, right, because for instance, to understand this expression, you need that if this is in LT, then the gradient needs to be in LS. So this expression is bounded because that's given by the Holder inequality. That explains that the B is taken in W1S and the tau in that space. Similarly, explanation for that. So those integration by part formula are key formulas in the derivation of our weak formulations, what I'm going to explain for the three examples. The details of each model are going to be decreasing because of time. I will spend more time in the first model and then less time in the other two, all right? So the first model is the coupled Darcy and heat equation. It has to do with the distribution of the temperature of a fluid in a porous medium. That's the reason you have the Darcy equation here, with incompressibility for velocity, U is velocity, P is the pressure, and a Neumann condition, a normal component of the velocity equals 0 on gamma. And that is coupled with the heat equation, which is a convection diffusion equation, which depends on the velocity coming from Darcy. Similarly, the viscosity in the Darcy problem depends on the temperature coming from this equation. So that's why it is a couple heat and Darcy equation. So here the notation that we're using, use velocity of the fluid, P is the pressure, bar phi the temperature, U is viscosity, K is thermal conductivity, and F, boldface F and F are external forces acting for each model. So the interesting part of the model is the fact that they are a couple. Otherwise, you can solve this independent of that, right? But then here you need the velocity coming from that equation. So since I'm interested in mixed formulation, I should have said this before, mixed formulation has to do with the fact that you introduce, in addition to the original formulations of the problem, you introduce other unknowns depending on that, or depending on the integration by part formula, or depending on some physical interest. For instance, if you're dealing with the heat equation, certainly you're interested in the temperature, but you may also be interested in the gradient of temperature. If you are dealing with an elasticity problem, you are interested in the displacement, but you might also be interested in the stress. And the stress is a new variable introduced in the formulation. As well, you might be interested in the flux, in the traction in that problem, all right? So mixed, in my concept, means introducing further unknown depending on the original unknowns, but also depending on some physical behavior. So that's the reason I'm introducing here what we call the pseudo heat flux, which is this sigma equal K gradient of bar phi minus phi times U. And because of the incompressibility condition, when you take divergence of that, phi, bar phi times U, you just get the convective part. And of course, if you take the divergence of that, you obtain the Laplacian. So the equation then can be written, instead of reading it in this way, as a second order equation, you just write it in a first order by introducing this auxiliary noun sigma. So you get the divergence of sigma equal that, and then your system, now your coupled system, can be written in this way. Darcy is still the same. We haven't done anything there. Actually, Darcy is already written in mixed form because the velocity is expressed instead of the gradient of pressure, right? But now the heat equation, as you can see, is of first order because we introduced this sigma equal to this, and then you get the equation itself, the equilibrium equation or momentum equation, I think, is divergence of sigma equal minus F. All right? That's the main ingredient of doing mixed formulation, is introducing this further unknown. One advantage, and among many others, but one advantage that one might obtain by doing this is the fact that because of this variable sigma here, one could obtain the gradient of the temperature in terms of this new unknown sigma and the bar phi and U. So that means that you don't need to make any numerical differentiation to obtain an approximation for the gradient of temperature. So that's one advantage of using this mixed scheme. Then you test against tau in order to get the fully mixed formulation. We test what we will call now the constitutive equation, which is going to be that. So we test this against tau in the same space where sigma is going to be looked for. So You obtain that, and we are going now to see two things, how to integrate that piece and what is the meaning of that. So then is when the Cauchy-Schwarz and Holder's inequality come into play, because then you observe that in order for this to be bounded, in order for this integral make sense, because of Holder, first Cauchy-Schwarz inequality and then Holder, you get that this is bounded by the norm of phi in L2 L and U in L2 J and the L2 in tau. All right? So that means that initially we are going to look for bar phi in the L2L space, U in L2J and tau in L2. And again, for this first term, we observe because of Cauchy-Schwarz that we need sigma in L2 and initially gradient of bar phi in L2. But then we apply one of the integration by part formula that I wrote in the preliminary section. So we integrate by part this, and then we obtain, integrate by part this piece, so we obtain that. And because of the boundary condition for bar phi, which is chosen to be 0 for simplicity, and then you obtain this is minus phi divergence of tau. So while in the beginning we assume that gradient of phi is in L2, that means 5 in H1. However, after integrating by part, we realize that actually we don't need to look for bar phi in that space, but still only in that one over here, L2 2 L. But then, for this expression to make sense, you need then the divergence of tau be in L, the conjugate of 2L, all right, because of Holder. Therefore, that's what I'm saying here, divergence of tau is in the conjugate 2L prime conjugate of 2L. And then this is another reason, again, because you need that H1 be included there, so that imposes this inequality that we wrote at the beginning. And because of the existence of solution for a Neumann problem that I'm not writing it here, but that we need for the analysis, it is a Neumann problem where you look for a solution in W1S. And that Neumann problem, in order for it to have solution, you need some restrictions on the indexes. So 2j less than or equal to 4 for n equal 2, and 2j less than or equal to 3 for n equals 3. So when you play with the indexes, so finally you arrive to the feasible indexes that you can, the feasible range of the indexes that you can choose for your problem. If it is 2D, we have a range for each one of the indices that we are going to use. Rho is 2L, bar rho is the conjugate of that, R is 2J, and S is the conjugate of R. So we obtain, this is a bit just algebraic manipulation, you get some ranges for those exponents. And surprisingly, for 3D, you just get on one possible choice. And this is obtained in several other examples, but it is not a general rule because there are other examples where you do have ranges also in 3D. So don't get enthusiastic that we are going to have this in all cases. This is just for this case. So then we are looking for solution bar phi in L rho, U in L R, and tau in H deep bar R. Remember that the variance of tau has to be looked in L to L conjugate, and to L conjugate is what we have called bar rho, all right? So those are our spaces. In this way, the first equation now, I'm looking here for the weak formulation for the heat equation. The first equation becomes this equation here, which you look for sigma, right, and bar phi, so define this for all tau in that space. And then you also have the equilibrium equation, the divergence of sigma equals something, so then that is tested. Since the tau is already here, it makes sense to look for the sigma in the same space. So that means that the divergence of sigma is going to be in L bar rho, and therefore the psi testing it is going to be in L rho, which is the conjugate of bar rho. All right, again, Holder inequality here. So finally, you arrive to the mixed formulation for the heat equation, in which given the velocity, then you look for sigma in that space and bar 5 in that space, satisfying these two equations here. And I have written in red this because this can be seen as a perturbation of the problem, including A, B, and B. And this is the classical structure of mixed formulations in what people call the babushka-breathy theory, that they have this form, A, B, and B. When A is symmetric, we are not assuming symmetry here. In the particular case, it is symmetric, but in general, it might not be. But if A is symmetric, then the solution of a problem involving A, B, and B, in this way, forget about that for a moment. The solution of that problem corresponds to a saddle point problem of a functional defined in terms of A and B. So that's the reason why we used to call all the problems involving this structure saddle point problem, even if they are not saddle point. Right? And for the Banach spaces, we still call them saddle point problem. But be aware that that's only true in the Hilbert case and when A is symmetric. All right? Okay, then knowing that the U has to be in LR for the heat equation makes sense, then when we look now to the Darcy equation, okay, we know already that, and that is a constraint. So therefore, when we test this equation, we have to make it so that the testing, it's allowed. And therefore, since this viscosity, I didn't write it, but say now this viscosity is assumed to be bounded on smooth. So basically, for when we test this, if U is going to be in LR, so we need to test with something in LS, with S the conjugate of R. All right? And because of this condition here, the divergence of U equals 0, I mean, and the boundary condition, which was this normal component equals 0, so then we introduce this space X2, which is what we call H0 R div R, the vectors in HR div R with normal component 0, and then the test is going to hold with this X1, which are the function in HS div S with a normal component equal 0. So everything makes sense. Now if we test this equation against a B in X1. So we get and then this gradient of P times the B, the integration by part, we use the second one that I mentioned before, all right? And that gives rise to this integral of over omega of P times the divergence of B. So that's our first equation, and as you can see, the U is going to be in HR div R with normal component 0, and the B is in HS div S with normal component 0, and R and S are conjugate to each other, all right? And then, sorry, then compressibility condition, since the U has a divergence in LR, so we tested again a Q in LS. And that is the second equation is going to be integral of Q times divergence of U. It's going to have the same expression like this, the same algebraic expression, but they're holding in different spaces. One involving HR div R with LS, and the other involving HS div S times LR, all right? And another technical issue, because of the uniqueness for the pressure, because if the pressure is constant, this vanishes. So in order to have a unique pressure, we introduce then the space for P in those P in LR with mean value 0. And similarly, the test function Q is going to be in LS with mean value 0. So finally, we arrive to this, again, saddle point problem. It's not a saddle point, but we used to call it that way, in which given bar 5, now you look for U and P in those spaces X2 times M1, such that this equation is satisfied for all B in S1 and for all Q in M2. And this is the more general case that you can find in Banach spaces for a typical saddle point problem, in which the bilinear for B1 and B2 are different. Remember, in the other case, they were the same. These are different. So summarizing, we have then our couple problem with the two equations for for the heat equation for Darcy. Here we have the typical structure of the saddle point with the same B, and here we have the more general one with B1 and B2 different, although they are algebraically the same. P times divergence, all right? Pressure times divergence, but they are acting on different spaces. So because of the couple structure of this, we propose a fixed point strategy. So first we define the operator that given a bar phi, you define the solution of that, and then the other operator that given the u, you define the solution of that, all right? So those are the operator t tilde acting from L rho into H0R div R, so that to each psi assigns t tilde of psi equal u tilde, where u tilde time comma p tilde is the solution of this generalized saddle point problem. And similarly, now we define the operator hat t that given a velocity assigns the solution of this problem here, in which you have the typical saddle point structure. So it's very easy to see then that the whole coupled problem can be written as a fixed point equation in terms of the t tilde and hat t, which is given by this t operator given by t tilde of hat t of w. So the solving the coupled problem is can be seen to be equivalent to find a fixed point of the operator t. I'm not going to spend time in explaining all the ideas behind the way this fixed point theory is handled, but I'm going to concentrate in the existence of solution for each one of the decoupled problems, the decoupled ones, all right? So first, the well-posedness of the operator defined by tilde, and here the key issues are that when you have a bilinear form A, and this tilde is the one here, right? In order for this, the main theorem says that you need basically that the operator induced by B1 be surjective, that the operator induced by B2 be surjective, and that the operator induced by this bilinear form be bijective, but in the kernel of either one. Basically, that's it. When B is the same, it's easier. You need that the operator induced by this bilinear form be surjective, and the operator induced by this bilinear form be bijective in the kernel of that operator B. All right. So that means that then, in order to prove that, one had to show this what we call in subconditions, which means that you have to prove that given a W in the here K1 and K2 are the kernels of each bilinear form, the kernel of B1, the kernel of B2, all right? And it turns out to be those functions in that space with free divergence, in each case, both in different spaces, but with free divergence. So then we need here to show that this supremum, given a W in K2, the supremum over the other kernel has to be bounded by a constant time the norm of W. All right? So if we look at that expression here, is the integral of mu times W times B. Think of the easy case, which is the L2 case, which is Hilbert. If it is Hilbert, this is very easy, because then when you bound, when you want to get a lower bound for this, okay, you choose, given the W, you choose the B equal the same to the W. Forget for a moment for this mu, because it is bounded, all right? So let's think that we have integral over omega of W times B. In the Hilbert case, L2, given the W, you can take B equal W, and then you get the norm of W squared in the top, and here you got the norm of W in this part, and therefore the equation of that gives you the norm of W. So then you have the proof with alpha tilde equal 1. Right? That's in the Hilbert case. But we are not in the Hilbert case because the spaces where this is acting are different, right? We are K1 and K2, so we have to make a proper choice in order to bound this and obtain that, we have to make a proper choice for the B that we are going to take here in K1. And that has to do with what I mentioned before. We are going to use the well-posings of a Neumann problem in which you have certain restrictions for the indexes, and that Neumann problem allows to define an operator ds going from Ls into Ls, which has this property here, that is free divergence, and that normal component equals 0. So then what we do is, given a W in Lr, this is well known, you define the function modulus of W to the power R minus 2 times W, and that's very easy to prove that this Ws is belonging to Ls. Given now that Ws, you put it here, and then you take the operator ds of that Ws. This is what I'm saying here. So taking, in order to bound this, we bound it below by choosing a particular B, any one. And the convenient one here is this one here. Taking B equal ds of that Ws. And this operator here, as in addition to this property, has this property here, that the integral of W times ds of Ws is equal to the integral of just the product of W and Ws. And that's also very well known that when you do that, then you get the product of the norms of W and the norm of Ws. All right? And when you pick that B equal that operator is bounded. So therefore, the norm of that x1 is less than or equal the norm of ds. So, but the reciprocal of that, 1 over that, is greater than or equal 1 over that norm. So then you get that the constant alpha tilde is precisely the reciprocal of the norm of ds, because then, right, you have that, the product, and then below you have the Ws again, so you get the inequality with that constant alpha. It's a bit technical, but what I'm what I'm trying to emphasize is that the choice in doing this, which in the Hilbert case will be very easy, in this case we have to go through an auxiliary operator which has to do with a Neumann problem whose existence of solution is restricted to certain ranges of the indexes. All right, that's what I want to show. So, and then I was saying that the main theorem requires that that M subcondition for A and also M subcondition for B1 and B2, and that means that the operator induced by B1 and B2, they need to be surjective. And being and being surjective is equivalent to asking that the adjoint of them be injective and of closed range. The students on my short course, they should know this. I was telling about this all along the week. So anyway, so therefore, I'm proving then the M subcondition for BI equivalent to prove that the operator induced by that, the adjoint of it is injective and of closed range. And that is equivalent to show this inequality over here. And this, I'm not giving any detail, but it can be proved by using another auxiliary problem in which the data of that auxiliary problem is the given Q that we take here. All right? So finally, one is able then to prove, according to that, the well-posings of the operator T tilde. How much time left do I have? We started at what time? 25 minutes, okay. So I'll relax a bit. All right. Is it too boring? No? No? Are you sure? Carlos? Is that Carlos? No. Carlos, it's okay? No? Complain to Yuri. All right. So, in order to prove now that the operator induced by hat T is well posed, it's very similar and even easier, because in this case, I also mentioned this in my short course yesterday. This A is elliptic in this particular case, because the AT in that space, because the kernel now is again free divergence, and A is again the A of tau and tau is the norm of tau squared, and when that holds, that we call elliptic. So the imp subcondition for A is very straightforward to be obtained. And then for the for the binomial for B, again we have to prove an imp subcondition, and similar to that one, that goes through the solution of an auxiliary problem in which the data is the given psi over here. So it's also able to prove that. Then, having proved that both the coupled problems are well posed, what we do now is, in the particular case of the heat equation, we just plug all the bilinear forms into just one. And here it comes the fact that when you prove that you satisfy the Babushka-Bressy theorem, which is we just mentioned, that is equivalent to verify the hypothesis of the well-known Lax-Milgram lemma for the whole operator, for the whole bilinear form, if you add both equations. So what Babushka-Bressy does is that because of the structure of A, B, and B, it's not straightforward to prove that the whole bilinear form is going to satisfy the imp subcondition which is required by the Lax-Milgram lemma. So Babushka-Bressy gives a better way of doing that, which is proving that B is surjective and that A is bijective. The imp subcondition for B, the imp subcondition for A. So then, because of finally the things are equivalent, we have actually the global imp subcondition for A, and that means this inequality here. So, but we had a perturbation of our problem, so then we define this new bilinear form, which is including the perturbation. And then it's easy to show that for a sufficiently small velocity, which means this inequality here, this operator, this bilinear form AW satisfies the hypothesis of the Lax-Milgram lemma, and therefore the whole problem involving the perturbation is well posed, but under a restriction on the given velocity. So this is not going to work for large velocity. All right. So further remark concerning this model, one can prove that the operators T and T tilde and T are Lipschitz continuous, and therefore the whole operator T is Lipschitz continuous. That's very easy to see. One applies the Banach fixed point theorem for the continuous case. But in numeric analysis, we are also interested in the case in which we consider the same problem, but instead of looking at the continuous space, we look at finite dimensional spaces. So we look for an approximation that we call the Galerkin method, the Galerkin scheme. When you choose those finite dimensional spaces as piecewise polynomials, that's what we call the finite element space, finite element method. All right? And in this particular case, we use what they call the Rabier-Thomas spaces, in which we approximate locally on each triangle of the domain, we approximate the sigma, the pseudo heat, by a vector polynomial of degree k plus the vector x times a scalar polynomial of degree k. That is the usual form of a Rabier-Thomas space. And it is shown that with that kind of spaces, the scheme is stable. That means that they have solution, unique solution, and it depends continuously on the data. So now, when you go to verify now the Babushka-Bressy theorem for this discrete case, so you're going to do the same in the sense of proving bilinear form B satisfy the imp subcondition, but now with the finite element, with the finite dimensional spaces. So now everything is discrete. And in that case, we require that the constant involved be independent of the dimension of the finite element subspaces, because the idea is that that dimension is going to increase. So in that case, one has this discrete kernel of B1 and B2, and then in order to follow basically the same idea, here I'm explaining that, the same idea when we try to prove that imp subcondition for A, I cannot take just ds of WSH, even if the WH that I'm taking originally is in the finite dimensional space. When I apply to it the WS WH comma S, so that it becomes in LS, and then I apply the operator ds, that's going to be in LS, but it's not going to be necessarily in my finite dimensional space. And that's why, in addition to that, when I'm trying to explain the same idea that we just did for the continuous IMSAP condition, all right? Choosing, in that case, given a W, we just choose to get the lower bound of the supremum taking the S of that W. But that doesn't work in the discrete case because the ds of that is not going to be in the discrete space, all right? And that's why we need to project. This is the projection, the orthogonal projection in L1 to KHK. This orthogonal, of course, is between, because, of course, here we don't have in a product. But the definition of that projector is exactly as if it was the L2 orthogonal projector, the same definition. Okay, so in order for the same argument from the continuous case to work in the discrete case, the first thing we needed to do is to define this projector. And actually, we found out that it was the first time this was going to use in this context, and that projector, the bounded, the fact that this is bounded wasn't proved. And we were able to prove it only in 2D. So in 3D, proving that this projector is uniformly bounded in the LS norm, I'm talking the LP norm, LR norm. In L2 is trivial. In L2 it's certainly bounded. But in LR, it wasn't known to be bounded, and we were able to prove that it was bounded, but only in 2D. So there is a technical difficulty in 3D. So in that, we were able then to prove the IMSAP condition, the discrete IMSAP condition for A, and following another argument, we were able to prove the discrete IMSAP condition for BI. In the case in which omega is not convex, which is also included in our analysis, we need an extra regularity for Neumann problem, and that adds another restriction for the indexes in which we are going to look for the unknowns. And in this case, certainly, we apply the Brouwer and Banach theorem, first for existence, and that for uniqueness, Brouwer for existence, and Banach for uniqueness. All the details can be found in this paper recently published in the IMA Journal of Numerical Analysis. So that's all what I'm going to say about the first model. The second model is what we call the Navier-Stokes-Brinkmann problem. It has to do with the modeling of a viscous fluid within a porous medium. It's basically Navier-Stokes plus a zero-order term here, all right? This is not coupled, but it's still nonlinear because of that. Incompressibility condition, Dirichlet condition for velocity, and this condition for the uniqueness of the pressure. All right, a very, very simple, very well-known problem. So U velocity, P the pressure, E of U is the symmetric part of the gradient, also called strain rate tensor. Eta is the scale inverse permeability of the porous media. For me, it's a constant. Don't ask me what it means. That means exactly. Lambda, the inverse of Riemann numbers, same comment. Mu, the viscosity, okay, constant. F, external force. U, Dirichlet data, incompressibility condition. Because of that, well, you need a restriction on the Dirichlet data. It has to satisfy this condition. And here we need to use the deviatoric tensor, which is making a tensor with trace equals 0. So just subtract 1/n, the trace of the tensor times the identity. All right? So that's the setting for this Navier-Stokes-Brinkmann problem. So in this case, again, we are doing mixed formulations. We like to introduce further unknowns of interest, and then we are introducing the strain tensor as an unknown, which is the gradient minus gamma, and gamma is the vorticity, the skew symmetric part of the gradient of velocity. So in doing that's first unknown. And then we also introduce the stress tensor, in this case, which is lambda mu t minus u times u minus p times the identity tensor. In that way, our Navier-Stokes-Brinkmann equation can be written very simply in this way because of that definition. So we have that, and we take the deviatoric tensor to that, and the deviatoric tensor of the identity is 0. So we just get this. The deviatoric of this is the same t because the trace of t equals 0 because of the compressibility condition. All right? And we get that. And you can take now the trace of that, the trace, a metric trace of sigma, and then you obtain a formula for p, because here you will get np. So the trace, p can be obtained in terms of sigma and u in this way, because the trace of that is 0 because of the incompressibility condition. So you are able to obtain the pressure in terms of sigma and the velocity. That's another advantage of this mixed formulation, that you obtain an expression for the pressure, so you can eliminate the pressure for your formulation. So in this way, we reformulate the model t plus gamma equal gradient of u. This is the now the constitutive equation. This is the momentum equation, and this is a condition now, the uniqueness condition on p was mean value of p equals 0. Now it is transformed in the mean value of the trace of sigma plus u times u. All right? And there is the condition. And here, I think I'm going to rush a bit. And here we integrate by part. Again, testing against tau, you get that. And now the integration by part of this, according to the formula, we assume that in order to apply our integration by part formula. So that remains the same. And this becomes minus u times the divergence of tau. So we are going to look for t in L2, gamma in L2, and u in LR prime, where R prime is a conjugate of R, and this tau is in H deep R. That's initially, all right? And T, which is the strain rate tensor, because of the compressibility condition, the trace of it is 0, so we look for that in that space here. The tensors in L2 with null trace, and gamma, which is the vorticity, which is skew symmetric, so we look for it in the L2 space with skew symmetry, all right? So then, testing again S, the constitutive equation, we get that. And this term here, so we apply Cauchy-Schwarz plus Holder, and when we do that, so we get u in L2L, u in L2J, and S in L2. But of course, this u is the same, so of course that means that u is in the intersection of that, so finally we take L equal G equal 2. That means that we are going to look for u in L4. So R prime is 4, and that means then that the conjugate of R prime, which is R, is 4 thirds. So that means that the space H deep R becomes H deep 4 thirds. All right, with now a specific index. And testing again L4, the momentum equation, you get this here. And here we have an interesting thing. Well, and then the symmetry of sigma is tested again the skew symmetric. That's very well known, right? That tensor is symmetric if and only if it's orthogonal to the skew symmetric tensor. So that's what we are imposing here. And for the analysis, we just use a decomposition of this H deep as H0 deep plus the multiples of the identity. And this H0 deep are those tensors with mean value 0 for the trace. All right? That's another technical reason to do that. So after all, we arrive then at this formulation here. These spaces for vector t, which involve t and sigma, and vector u, which involve u and gamma. So we have this structure here. And I've written in red this because, as you can see, all this piece in red has the saddle point structure in the general case, with B1 different from B2, because acting on different spaces. But if I put together all these red bilinear forms, it's just one bilinear form, which I'm doing here. Well, here is the definition of each of the bilinear form over there. So if I put together A, B1, and B2 in just one boldface A, we arrive to this. And this is what this structure here now, in which this has a saddle point structure, but now together with that B and that C, it's what we call a perturbed saddle point problem. Why perturbed? Because of this C over here. That's the perturbation. Because if we had only this piece here, up to here, that would be just the usual saddle point. But because of that, it's perturbed. And surprisingly, for this kind of structure, in the Hilbert case, it was well known, the theorem. But in the Banach's case, it wasn't known, and so that's something that we had to do. And we were able to prove then a theorem, which is in this paper, with, by the way, with an undergraduate student. He was an undergraduate student, and we proved the theorem that says that if the bilinear form A satisfies the in subcondition with respect to the first component and the if subcondition with respect to the first component, those two conditions, what they are saying in the kernel of B, okay, in the kernel of B, those two conditions are saying again that the operator induced by this is bijective in the kernel of B. And if B satisfies this in subcondition, that is saying that the operator induced by B is surjective. So basically are the same conditions of the non-perturbed case, all right? But you need, in addition, that A and C be positive semi-definite and that C be symmetric. So this only works in the case that H, we have here H and Q, and also H and Q, all right? Same spaces. Corresponding assumptions on A, B1, and B2, which correspond to the general Babushka-Breathitt theory, which I referred to that classical paper from 1988 that was made that for the A, B1, B2, and use a fixed point strategy. Again, we arrive again to this, so we look for the operator that given a W, we put a W here, so we solve this linear problem where this is seen like a perturbation, and we analyze this with the theory of our theorem concerning perturbed saddle point problem. So the Navier-Stokes-Brinkmann equation then can be written as a fixed point equation in this way, and all the details are found in this paper, which is going to appear soon. And this is another undergraduate student, and this is a collaborator from Monash University in Australia. I got 5 more minutes. All right, this is going to be fast. No, I can tell a joke. You choose. Bolsonaro, Boris, Lula. All them. Well, the joke is always the same. It's only the changes of the story. Okay, be serious now. Okay, the chemotaxis Navier-Stokes problem is a model, I've been told, it has to do with the cell movement driven by a chemical signal within a fluid. Basically, it's a Navier-Stokes equation which depends on the cell concentration in some fluid, plus a convection diffusion equation of that cell, which depends on the velocity, but also depends on the concentration of the chemical signal, and a similar equation for the chemical signal. Okay, so 3 equations coupled with Dirichlet boundary condition. I'm not going to explain all the detail, but okay, here we have velocity, pressure, cell density, chemical signal concentration, fluid viscosity and density, diffusion coefficient of each case, consumption rate for the chemotaxis of U and gamma, and so on, and certain data, source function, and the Dirichlet data. Again, mixed method, we introduced the velocity gradient as a new unknown, and we introduce a kind of what we call a Bernoulli type stress tensor as an auxiliary noun, which is this sigma over here. In that way, our first equation, the Navier-Stokes type equation, can be written in this way, with again the pressure expressed explicitly in terms of sigma and U. And because of the uniqueness for the pressure, we need this condition for that term over there. For the cell and the chemical equation, we do similarly. We introduce the solid stress for the cell and the chemical concentration gradient as a further unknown, so that those equations can be written in this equilibrium form for the cell concentration and for the chemical concentration. So finally, okay, this is the reformulation of the model in mixed form, all the equation for the Navier-Stokes type equation, all the equation for the for the cell concentrations and all the equation for, these two equations for the chemical signal concentration. And now on spaces we do formulation, and here there is a novelty with respect to what we were doing in the other two examples, that now in our analysis necessarily has to appear this space HR, not div R. That's what we had before. We got into HR div J with R greater than or equal to J. So at first sight we thought, okay, this is not going to work. But then, thanks to some embedding of Sobolev spaces again, the im subcondition and so on could work similarly as done in the other cases. So we went through it. So, and here is the other spaces for the other unknowns, HS div S, LR, and LL. And again, in this case, because of technical reasons, for the L2, for the 2D case, we have ranges for J and L. But for the 3D case, you have only one possible choice. So one possible choice where you can look for the unknown. So the final structure of the problem is this one here. This is for the Navier-Stokes type equation. When you are given a U, for instance a W, then this becomes linear. So then this becomes an A tilde with this and that. Is a typical structure of the saddle point problem. This is already a typical structure of a saddle point problem, and here we have the more general one in which B1 is different from B2. And all the other terms are perturbation that depends on the other unknown. So this term here explains the coupling, and this one here explains the coupling between the three equations. So that means that we define suitable operators, and then we define a fixed point operator to write a fixed point equation. So here are some technical comment. As when you fix B and B here, this U equal that one, then that becomes 0, and that this in subcondition, I will just mention that in the case of HR div J, this in subcondition, it's possible to prove it similarly as we did it in the other case, but because of this embedding of W1J continuously into LR, okay, that was possible. So fixed point strategy, and this is in another paper which is recently submitted with some collaborator, and this is a PhD student recently. So in order for you to believe me that we have made all numerical experiment in all three examples, I'm just showing just a short example here of the chemotaxis case in which you have, here we add the time variable, so we are able to show 3 different times. We have a concentration of cell here, a concentration of chemical signal here at some time, a second time, a third time, and you can see that the cell is attracted by the chemical, and finally they are all disappears somehow. All right, or merge. So computed magnitude, velocity, cell density field, and chemical signal concentration field at 3 sequential times. Finally, concluding remarks. In all this mixed formulation and many others, the choice of spaces strongly depend on the kind of non-linearities involved. Second, existence and regulators of solution and PDEs play key roles in our analysis for the in subcondition and so on. Injection between Sobolev spaces come also into play. Saddle point and perturbed saddle point problems in Banach spaces among the resulting formulations. Brouwer, Banach, and Schroeder fixed point theorems are applied. Numerical experiment are much more generous than theory. What I mean with that the theory works because of the fixed point theory. Finally, one is able to prove things for sufficiently small data, right? But when we do the numerical experiment, we don't care much about that, and we just run any experiment, and we don't check those smallness assumptions because it depends on constants which are unknown, constants that come through the analysis. But the numerical experiment, as I mentioned here, are much more generous than theory. And even remember the first example that in 2D, the discrete analysis was depending on the fact that one projector was bounded. We were able to prove it only in 2D. In 3D, there is no proof for that. but still the numerical experiment in 3D work perfectly. So, and open problems, well, here I'm saying, avoid or diminish the smallness data assumptions and stability of orthogonal projector in 3D. And now I finish, Lucas. Related works concerning these ideas. For Boussinesq problem, we also obtain, it is also obtained that. For a stationary Navier-Stokes problem, for a steady-state model of fluid cell bed, is a joint work that we did with Yuri. For a stress-assisted diffusion problem, it's also possible to obtain that formulation for nonlinear transport. Also, we obtained that. So thank you very much for your attention. And that's
All right. Thank you very much, Gabriel, for this very nice talk and all these very nice, powerful results that you've shown us. So do we have questions, comments, concerns, ideas, suggestions, criticisms, jokes? Well, I'll start with a quick question then. Gabriel, you mentioned at some point that you needed the Neumann problem to get through the analysis and eventually prove existence and unicity of your solutions. And when you bring the Neumann problem, there are restrictions for the ranges of the exponents of the spaces. So it might be, I think you mentioned on your final slide, that it might be that the physics does not allow you to do that.
maybe, yeah.
So what happens? What do you do in those cases? Is it a technical problem that does not allow you to carry on with this kind of analysis? Or is there an essential problem on the physical model?
I actually don't know about the physical model much, but I would say that we used a result given the existence of a solution for a Neumann problem, and which shows that far from, outside that ranges, there is no solution. So it is a technical result that allows us to use that in that specific range. And it is proved by the people who did it that outside that range, there is no solution. So doing it in this way, we are somehow stuck to that ranges. So. But still, as I said, the numerical experiments are right. So are the opposite to the government. You see, government. I mean, to the opposite to the program of the government. They promise a lot of things, but they just do a little. Here is the opposite. We are able to prove a little, and we can do a lot of things numerically.
That's more generous, right?
Bad joke, anyway.
Yep. Do we have other questions, other comments? I'll do another one then, final one. This is a small one, not sure if it's even a good question, so I apologize in advance. So it's a more philosophical question. When you have Navier-Stokes equations and nonlinear terms, the nonlinear terms can become strong. And it depends all on those parameters that you pointed us in your slides. At some point, physics will tell us that there are multiple solutions. You could have two possible solutions for the flow. Where in the analysis would that appear? Is it the loss of ellipticity on the bilinear forms that is the symptom of the fact that unicity is lost?
I would say that it will appear first in the derivation of the wave formulation where you handle those terms. But because, as I showed, when you apply the Holder inequality, depending on the power of the nonlinearity you have, you are going to obtain different indexes. So my conjecture will be that you will get trouble first in the definition of the indexes where the unknowns are to be thought. You see, it's and perhaps also later on in the proofs of some of the IMSAP conditions.
Okay, all right. Very good. Any more questions? I think we should thank Gabriel again for this very nice
Thank you very
talk.
much.
And if I'm not mistaken, we have coffee break now. Yep, thank you. Thank you very much. Sorry? We have to be back here at 11, okay? Thank you.
Okay, welcome back. Okay, again. Welcome back, everyone. Now the next speaker to this plenary section is Claudio Honor Oliveira Alves, professor at Universidade Federal de Campina Grande. He is well known in his work, by his work in partial differential equations of the elliptic type. And I'm sure to say he is one of the finest in that area. So, and I am happy to tell you that Claudio Honor has got his PhD here in the University of Brasilia, so we are very proud of you. And having said that, Claudio Honor will talk to us about the existence and multiplies of normalized solution for some classes of elliptic problem. Thank you.
Okay, thank you very much, Matufu, by introduction. I am very happy to be here. Okay, all time that I came back to Brasilia, I feel very happy because as Matufu said, I made here my master in doctorate with Professor Josevaldo, and I had here very happy moments. Okay, thank you for invitation. Thank you, Zu, for your attention and with me, okay? And today I will talk about the existence and multiplicity of normalized solution for some class of elliptic problems. And here I show for you the general problem. And we intend to find one solution of this elliptic equation, but in your case, our solution must satisfy one prescribed L2 norm, okay? And here, our potential V is one continuous function, and F is one continuous function, and these both functions, of course, will satisfy some technical conditions. Okay, in this talk, I will show for you some recent results that I wrote with some colleagues, okay? We have one paper with Xiaoji in your friend Olympio. We have another paper with Xiaoji from China and Olympio. Another paper with Xiaoji. I have one paper alone involving this type of subject. We have two papers with one colleague from Vietnam. And finally, another paper with Chen from China. Okay. First of all, I would like to talk a little bit what is the motivation to start this type of problem. And when did we study the existence of solution for nonlinear Schrödinger equation type 2, there is one important physical law that says that the mass of the trajectory is preserved. What this means? This means for us that study PDE, that the L2 norm is preserved, okay? I will try to draw here one picture. One Okay. Of course, when we study the nonlinear arithmetic equation, one famous type of solution is the standard wave solutions. Okay? Is one solution like that in blue. When you take this type of solution and you put here into and compute, okay, the calculus, you will see that this function u here must satisfy one elliptic equation like that. This here. Okay? Okay. So, this type of solution, normalized solution, okay? But before to continue my talk, it is necessary to say there is two type of problems. When you don't fix the L2 norm, you say that your problem is free mass. But when you fix the L2 norm, in general, the people call the prescript elliptic problem. Okay? When the problem is free of mass, in general, you find a very rich literature involving this type of the situation. But recently, the problems involving the L2 norm prescribed is increasing, okay? Because in fact, we are learning how to get this type of solution, because it's not so simple, okay? Here, I show for you some important reference that show why the normalized solution is important in the physical point of view, okay? This is the reference here. Okay, one very important reference in this area is one famous paper by Casanave-Lyons. In these famous papers, the Casanave-Lyons, the authors studied the problem one that I showed for you a few minutes ago. Casanave-Lyons consider the existence of solution for this class of problem here by assuming that this nonlinearity is of one specific way, like power, okay? Here, absolute value of u power p minus 1 times u. And of course, they consider the potential V is equal to 0. What is the strategy used by that authors? The authors try to solve this minimization problem here, and in this famous problem, it was proved the following. If you consider the case where the problem is L2 supercritical, okay, and what is the L2 supercritical? L2 supercritical is when the power P is bigger than to 1 plus 4 over n, okay? This is the definition of the L2 supercritical. In this case, Casanave-Lyons showed that this minimization problem is not solved. In fact, they proved that this minimum, IA, is equal to minus infinity. But in the same paper, the authors also consider the case where the problem is L2 subcritical. L2 subcritical is the case where the power p lives between 1 and 1 plus 4 over n. In that case, Cazenave-Lyons showed that this minimization problem is solved. And in fact, that minimum is strictly negative for some a positive. What is the idea? The idea is the following. The authors prove that if you have one minimization sequence, it is possible to find one very nice translation of the minimization sequence, such that the translation of that minimization sequence is, of course, one other minimization sequence, but you can prove that the new minimization sequence is strongly convergent in H1. Of course, if you have one strong convergence in H1, you have in your hand one solution for your problem. Of course, okay, you are solving this minimization problem here, you will find one solution like this. And in your case, it's very important to say, because I forgot. When do you consider, I will use the picture here. In this problem here, this number lambda is unknown, because this number lambda is get by the Lagrange multiplier. Okay, this is a very delicate point, because when you are studying the Schrödinger equation with free mass, you can choose lambda. You can choose lambda of one convenient way, and when you try to find the standard wave solution, you can get one elliptic problem. In general, it's strongly definite that you can use the Montagne-Pass theorem. It's the basic idea. But when you try to get the normalized solution, you don't know what is the value of lambda, because it appears as one Lagrange multiplier. Okay, after reading the paper do Cazenave-Lyons, I propose to my colleague Xiao Ji to consider the situation where in the left side of the equation appear one potential V. Because in the famous paper do Cazenave-Lyons, the potential V is equal to 0. What our goal? To understand what is the geometry on the potential V, such that we can prove the existence of normalized solutions. Okay? In that paper, we continue to study the L2 subcritical case like Cazenave-Lyons, and we prove that, in fact, there are 4 classes of potential that it is possible to find one normalized solution. You can consider the potential V periodic, asymptotic periodic. The potential V satisfies one geometric condition introduced by Rabinovitz, and the potential V can belong to one class of potential introduced by Barthes-Wang. For this class of potential, it is possible to prove the existence of normalized solution. What is the idea to prove? Of course, our inspiration is to follow the same strategy by Cazenave-Lyons, but of course, during this path, we find the challenge, okay, to get the solution. So our intention is to prove that the minimization problem for is solved. The idea is to consider that energy functional J, okay, and prove that this infimum is achieved. Okay. What is the first step? The first step is to understand what the relation between the infimum epsilon A with the parameter A. Of course, the parameter A is fixed, but it's very important to understand if I move the parameter A, the L2 norm, what happened with the infimum? In this case, we prove that this function, upsilon A over A squared, is one decreasing function. This information may be simple, but it is crucial to prove our one compactness condition. Here, I recall for you in all my talk, SA is this manifold here. This manifold is the L2 sphere intercept with the Sobolev space H1. Okay, this is one manifold. Okay, it's not the L2. No, it's not one sphere. It's one sphere only L2. But in the Sobolev space, we don't know what is the manifold. We prove the first compactness result. We were able to prove that if you have one minimized sequence, such that you know that the minimized sequence is weak convergence, you have the pointwise convergence, and you know that the weak limit is non-trivial, it is possible to prove that this minimized sequence is in fact one strongly convergent. It's a stronger sequence. This is a very important because, for example, if you know work with the elliptic problem invariant by translation, in general we use the Pierre-Lyon's result, and we prove in a lot of problems, elliptic PDE, that if you have a sequence and you have some problem with the weak limit, you change the sequence by translation and you get another sequence. This happened, for example, with minimized sequence, PS sequence, and so on. So here we say, if you get one minimized sequence, just that we know that weak limit is non-trivial, I am able to prove the strongly convergence. So with this information in your hand, we prove the existence of normalized solution for that class of potential V. After, okay, I go for one alone project. In this paper that I wrote alone, my intention was to prove the existence of multiple normalized solutions. Because in the literature, there are many papers, or not many papers, but some papers that prove the existence of multiple normalized solutions, but the authors assume, in the most part of them, that the nonlinearity is homogeneous, that is, f does not depend on x, or when f depends on x, they assume that f is radial with the variable x, because in that paper, the authors works on the H1 of the radial functions. Because when you work there, you get very nice compact embedding. Okay? And here, my goal is I want to work with one class of problem that the nonlinearity is not radial in the variable x. It is possible now to find multiple solutions. Here, we prove that. The motivation, of course, this comes from one paper due a Cal, where Cal proved that the geometry of the function h that appear in the right side of the PDE is strongly related with the number of solutions of one PDE, elliptic PDE, with free mass. Cal proved that the number of solutions is at least the number of maximum of the function A. Once that I know that result, I ask for myself, it is possible to get the same result here? The situation is totally different, because in the paper to Cal, the geometry that they work is the mountain pass geometry. Here, no. Here is one minimization geometry. It's totally different. It is necessary, in fact, develop one new strategy to solve the problem. So, here, in this paper, we consider one large class of nonlinearity. Okay, one large class of nonlinearity. In the most part of the paper, the author assumed that the nonlinearity is homogeneous, like this. Here, I try to avoid this type of property. So, in fact, we proved that when epsilon is small enough, the number of normalized solutions is strongly related with the number of the maximum of the function A. Okay? What is the idea? The idea is to, again, consider the minimization problem involving the problem that you want to solve. And if you have some experience with this type of problem, you know that the autonomous problem is very important. It is necessary to understand in details what happened with the autonomous problem, okay? So here, we prove one very, very important result. We prove that if you consider the autonomous problem like this, I recall for you that the famous paper do Cazenave-Lyons consider one specific case. And they prove that, in that case, if you have one minimized sequence, they prove that it's possible to translate to get a new sequence, and the problem is solved. Here, we prove that behind the famous paper do Cazenave-Lyons, there is more information. And we prove this compact result. We prove that, in fact, you can work with a large class of nonlinearity, and you can prove the same result that Cazenave-Lyons proved in that paper. Okay? Using this information, we go to the next step. What's the next step? The next step is the following. Here, we don't have in your hand the symmetry to help us to get some estimate. So, it is necessary to understand, if you don't have one strongly convergent, what we lost? So, here, we prove the following. If you have one PS sequence on the manifold SA, if you don't have strongly convergent, it is possible to find one number beta, such that this number beta does not depend on epsilon when epsilon is small enough, such that the L2 norm, okay, is bounded from below by that constant. That constant say for us what we lost in the L2 norm when the strongly convergence does not happen. This is a very important. This is one key point in your paper. After this key lemma, I was able with my colleagues to solve more difficult problems. Okay? This lemma is key, é key lemma, because this lemma, together with the compact result, permit to prove, in fact, the PS condition for your functional at some levels. Okay? And here, of course, I will avoid details. My intention here is not to show details. If you like this subject, you can find in archive, you can write for me, and I can send for you the preprint, or some of them are published. Okay, after this paper, I went to another problem. with a thing. And now our intention is to following. We don't consider here F depend on X. But we come back to work with here in the left side with one potential, V. Here, again, we work with the geometry introduced by Rabinovitz. In this moment, it's very important to recall that when you try to find the standard wave solution for free mass, there is one famous paper by Rabinovitz that Rabinovitz proved. For the case of the mass is free, it is possible to find one solution for Schrödinger equation when epsilon is small enough. What is the challenge here? It is possible to prove the same result by Rabinovitz by this class of solution. Of course, in the famous paper by Rabinovitz, the geometry is totally different, because there Rabinovitz used the properties of the mountain pass level, and using the property of the mountain pass level, in particular the properties of the Néraire manifolds, it is possible to understand the behavior of the mountain pass level with relation to parameter epsilon to prove, in fact, the existence of solution when epsilon is small enough. But here, we lose the mountain pass geometry. We are working with the minimization problem. How to do that? Here, again, we need to introduce new ideas, and in fact, okay, it was necessary to understand. Oh, of course, sorry. In the paper of Rabinovitz showed only the existence of a solution. After, in one paper that I wrote with Giovanni Figueiredo, that working here now, we proved that the geometry of the graph is very important, because if the points, the set of the points where the potential V achieve the minimum, if this set is topologically rich, it is possible to prove the existence of multiple solutions associated with the category of the Lucianic-Theorem. We together these ideas, and we proved that in this case, it is possible to prove the existence of multiple normalized solutions using, again, the category of the Lucianic-Theorem. Okay? And here, when epsilon is small enough, this is our main result. Okay? Of course, here, the potential V has one technical restriction here. For me, it's not so strong, because it's associated with the technique that we are using to show our solutions. And here, in some sense, we show again the concentration phenomena involving the maximum point of our normalized solutions. What is the idea? The idea, of course, motivated by the study made for the mountain pass level, we, in your case, so that this number here is one infimum, but in your case, it works like the mountain pass level. It was possible to prove that if we understand in details the behavior of this number upsilon epsilon, okay, we prove the same case. Of course, note that, for example, the mountain pass level is positive number. Here, our level, all of them are negative, all of them. So some estimate is not clear that happened, okay? So we begin our study to try to understand what is the relation involving the infimum that we need to solve with the autonomous case. Here we have one similar result involving the sequence, But here, I ask your pay attention, because here in this lemma, we don't have necessarily one minimizing sequence, but here one general sequence. The key lemma, using the key lemma, we prove this. Okay? In this type of problem is a very interesting, because, for example, in that paper that I proved the multiple solution by using the graph of the function 8, what is the strategy to prove that the solutions are different? You choose in the manifold SA sets where the barycenter of this function here is close to the maximum of the function A. And you minimize locally in this set. And by using Echelon, you prove that it is possible to find one local minimum in all that regions, and you, of course, can conclude that solutions are different. Okay? Here is the same, but we use the barycenter technique to relate the manifold that you are work as A with the set involving the minimal point of the potential V. Here, okay, we are following all paper that work with the free case. Okay? Oh, I look for one free case problem and I ask me, it is possible or no to get the same type of solution? Of course, there are a lot of that I don't know at the moment, if it's possible or no. Okay? So I invited you, if you like this, I am here to work with you about involving this subject. When you see in the literature, there is one famous paper due to Alpini-Feldman. The famous paper de Alpini-Feldman is after the paper due Rabinovitz. Rabinovitz studied the situation where the potential V has this type of geometry. Okay? Here, in your case, V can be 0. In the Rabinovitz case, V has influence strictly positive. This is the geometry doing Rabinovitz. And the geometry introduced by the Alpini-Feldman, they work with the local case. The local case generalize this geometry, because in the local case, the authors only assume that there is one region lambda such that the potential V has locally this type of geometry. Okay? So this potential can have this geometry at infinity, totally different of the Rabinovitz geometry. Okay. In this paper, famous paper, the Alpini-Feldman showed the existence of solution when epsilon is small enough. After, I wrote one paper with Giovanni and proved that, in fact, in that paper, there are more solutions, because the graph, the region on the potential V achieve the minimum. If this region is topologically rich, the number of solutions depends on the category of the set. Okay? So we get all this information and try to solve this. And we got the same result. We proved the existence of multiple normalized solutions, and the number of solutions is at least the category of the set where the potential V achieve it's minimum. Okay? This is one preprint. Okay? We are waiting for answer of the journal. But here, I would like to point out what is the big problem here. In this paper do the Opinifelme, the authors, when they work with the problem, the Opinifelme introduced one penalizing method. What is the penalizing method? The penalizing method is essentially the following. They consider one new function, phi theta, and they consider phi theta like this, ft, t less than or p, and here you put b0 of k, t bigger than or p, and fb of course equal to b0 of k to become this function continuous. So they consider one new nonlinearity like this. And they propose one new analytic problem involving this nonlinearity, and they prove that when f is small enough, there is one solution for the new problem. But what is the idea? It is necessary to prove some estimate involving the L infinity norm of calculate the L infinity norm in this, the complementary of the set lambda is less than of t, because when this happens, you get the original problem. You prove that the solution of the new problem is in fact one solution. But here, this term does not work well. We spend a lot of time to find what is the best penalization that we need to use here. And for my surprising, it's that. It's not more one linear perturbation. Because in here, we have one linear perturbation. For the normalization situation, no. You need to put that way, okay? So, with this information, new estimate appear, and we prove that it was able to prove the estimate and so on. Okay? But I would like to talk a little bit. Matofu, how my time? Okay. I would like to talk a little bit about the L2 supercritical case. This is a very important problem because I talked a few moments ago about the famous paper do Cazenave-Lyons. Cazenave-Lyons proved that the minimization problem is not solved. But the fact that the minimization problem is not solved does not say that there is no normalized solution for L2 supercritical case. Only say that this approach is not good to get the normalized solution. Okay? After 30 years, okay, Jian write one very interesting paper involving the L2 supercritical problem, and Jian teach how to work with this situation, and Jian show for us that it's possible to work with the mountain pass geometry on the manifold SA and prove the existence of a solution. Of course, it's a very interesting because in this manifold, we don't know if the manifold is planned. Because when you are working with the Sobolev space H1, you can work, for example, in lines. But here, no. It is necessary to understand what is the good path that you need to use in the mountain path geometry to get your solution. Okay? And here, Jan shows for us, there is one rescaling that works well, and that rescaling works like the path that we need to use in the mountain path geometry. This is a very interesting point. And here, okay, we have one beautiful, beautiful paper, okay? After the paper due Jan, okay, I work with Olympio and Xiaoji, one paper here. But, of course, there are very, very interesting papers in this subject. I say that the Jan is the papa of this subject, because it's a very interesting, the very good paper that he has involved in this subject. Sometimes I write the paper and send him. I ask Jan, what is your opinion? It's good or no? Okay, but it's a very good guy. In this paper that I wrote with Xiaoji and Olympio involving the supercritical case, okay, our main contribution was the following. We observed in the literature, there is no result involving the normalized solution involving, for example, in dimension 2, the nonlinearity with the exponential critical growth. And we decided to fight this situation, and in fact, we proved that there is normalized solution. This is the first paper involving normalized solution and exponential critical growth. For dimension n bigger than or equal to 3, we work with that situation, but there was no literature, some papers do Nicola solve. Okay? It's very important to say that there are papers involving the multiple normalized solution for the L2 supercritical case, and in this case, the genus theory is the main tool used. Okay? Here, I show for you some papers involving the multiplicity normalized solution, and we have another paper with Olympio. Olympio works a lot, and we have this paper here. And Xiaoji will visit Olympio next July, okay? I think that we will write 10 papers involving this subject. And here we have our contribution here. Our contribution of the multiplicity, of course, because when you consider the critical exponential growth, how we prove the multiplicity of solution, because in the literature there is no similar result. And then here we introduce one new way to get the multiple normalized solutions. Okay, we are working to finish it because it's closer to have lunch. Now, one very important question. Look, in all my talk, I mentioned papers in Rn. What happened when the domain is bounded? Okay? If you consider one bounded domain, the L2 subcritical case is a homework for my student in Campina Grande. It's homework, because you have a bounded domain, you have a very nice compact embed, and you solve. It's not difficult. But the challenge is to work with the situation L2 supercritical. Because I tell you a few minutes ago that Jian showed for us that there is one high scaling that is possible to work in a lot of problems involving the normalized solution in H1, but that high scaling move the bounding domain. When you try to use the high scaling, it's the domain is not invariant. When the domain is bounded, it's not invariant by that high scale. So I only know 4 papers involving bounding domain. 4 papers. Papers do Benedetta Pelati, né? E tem 2 guys, tem Hugo Tavares. But the main point is, when the domain is bounded, the framework is totally different. In general, the Mohs index is used there. In these papers involving bounded domain, right now, I am not able to understand. The technicality is totally different. It's very hard, okay? But I am from Brazil, and I don't give up. Once that I didn't understand, I create my new method to find one solution, okay? And here, in this paper with Shen, we introduce one new way to find normalized solution for bounded domain that does not use Mohs index and the uniqueness of solution in Rn. Because in some of papers, the authors, in some sense, project the solutions of this problem here. It is well known in the literature that this elliptic PDE has uniqueness of solution at least translation, okay? The authors take one solution of this problem and make one cutoff of this solution and try to find the normalized solution using this cutoff of this part of the solution. It's the computation, it's so hard. It's very, very difficult for me, regular person, okay? So, but here, okay, it's here I cite the Norris, Tavares, Vecini, okay? This is only this paper here involving this type. I send to Jian this. In one recent paper, do Jian, they cite our method has one promising method in this type of solution. Okay, I believe that. I will finish here. Thank you very much for your attention.
Well, thank you, Graduate Calajuno. Very nice talk and wonderful survey on the subject. Now I will ask the audience if there is some remarks, comments, or questions. I think this subject is too difficult. Oh, Olympio, please.
First of all, Claudio, congratulations beautiful talk, showing good
You are my
teacher
friend.
also.
You are my friend.
Claudio, can you tell for us what happened for L2? Critical number problem involving critical.
Not the situation L2, because
Yeah.
there is the classification of this problem are in three classes. The L2 supercritical, P bigger than 1 plus 4 over n. L2 subcritical, P less than 1 plus 4 over n. But there is the critical case. P is equal to 1 plus 4 over n. The situation critical, in general, you prove the existence of normalized solution when the mass is small. It is possible to recover because the L2 supercritical, there is one competition involving the power of the gradient. Okay, it's 2. In the right side, when you take make the computation, it's the same order, because here one very important inequality is due Nuremberg. How can I say? Do you recall the famous inequality? It's the inequality that you can prove that the LP norm is less than the one constant, L2 norm, 1 power, the gradient norm. Nuremberg. Thank you. Okay. When you work with the L2 supercritical case, when you use this, there is one computation. In order to overcome the difficulty, you assume that the L2 norm is small, and you can work again. Okay.
Any other remark? Questions? Oh, Marcio.
Yeah, you know, I don't know all techniques. So in the previous problem, when you have 1v times u, the question is just a curiosity. Are there researchers that put the lambda u in the other side, and then write v minus lambda u, and then give you some assumptions on v in terms of lambda, or not? Just a curiosity.
You are talking about this?
Yeah, exactly. When you add v, instead of giving several other assumptions on v, capital V, then you put on the right. Yeah, you can put it on the right, and then you're going to have lambda minus v, and then assumptions.
Okay. It's the situation, for example, when you assume that potential V change signal, or for example, when the potential V is negative. If the potential V is negative, you can rewrite here V as minus V, and you put in the right side. It is possible, okay? It is possible to consider here. In my previous paper, I didn't work with this situation, but right now, I'm sure you can consider the potential V negative once that the L infinite norm is small enough. Now I know the trick to make the machine works well. Okay?
Any other remarks? Comments? I have a comment.
Okay.
When we can have the pleasure to see your new methods for bounded domain?
Yes. In fact, after some months reading the paper, I saw that in all that paper, when the domain is bounded, the mass need to be small. Okay? So I observed that in the normalized solution, if you assume that the mass is small, it is possible to prove that there is one region in the Sobolev space that the normalized solution must live there. So I propose one new truncation, and we work with a new problem, and we prove the existence of normalized solution for that new problem. But in fact, that normalized solution lives in the region that the normalized solution of the original problem works, and after some computation, we proved that the normalized solution for the new problem is in fact the original problem. There is one truncation behind the argument. Okay? But it still hold for A is small enough, okay? When the norm, L2 norm is small. Because in the first moment, I have a doubt if the R result is good because we assume that the L2 norm is small. But in the literature, all that paper are published in calc of variation, JDE, and so on. I believe that. If that are there,
It's
I
quite
suppose
interesting.
that the referee don't criticize the fact that in your case the L2 norm is small. I hope.
Okay, let's thank again Professor Claudio No. Outstanding conference.